Right. So I'm sure most of you have seen energy balance somewhere before. I did it in my oceanography class as well. But we'll go into a little bit more details here because it's the dynamics course and we need a few more of the details. But we'll start with the same basic concepts. We'll first do the energy balance on the whole sphere. So it's a global balance, and then we will go into balance per unit area. So you'll see the switch happening. So if we want to consider the whole planet, then the first thing is to see how much solar energy is received. What is that determined by? Basically, sun is fairly far out, 150 million kilometers, so the rays are parallel by the time they reach Earth. And Earth is a sphere. So if we flash a light on a ball and look for the shadow is going to be circular, right? So the amount of energy intercepted by Earth is going to be determined by the disk area that the Earth projects to the Sun, which we saw in the last chapter. So here it is being shown as area pi a squared, where a is the radius of the Earth, right? Not a very big deal. And the albedo that we discussed in the last podcast mentioned the various surfaces. The ocean here is shown as white because, as we said, the albedo of the ocean depends on the angle of incidence. Can be very high when the sun is at a lower angle, but sun is overhead, then ocean can have a very low albedo and absorb almost all of the energy. Surfaces, obviously high latitudes like Greenland and parts of sea ice over the Arctic snow or Canada and Antarctic glaciers obviously are very bright, and you can see the albedo is at 0.7 to 0.8, so 70 to 80% of the sun's energy is being reflected back to space by these surfaces. We mentioned deserts being highly reflective, so you can see the Sahara, Middle East, Gobi Desert and so on, and there is the Himalayan glaciers here reflecting some, but it's not as bright as here because they are dirty. They are called debris covered glaciers, so they have a lot of rocks and sediments in them. Okay, and of course there is snow at high latitudes over Siberia and so on. With that distribution, then doing the energy balance is fairly straightforward. Again, we're doing a gross global energy balance first. The energy flux at the top of the atmosphere is S0, solar flux per unit area, watts per meter squared, multiplied by the area of the disk that's intercepting the energy. That gives you 1.74 times 10 to the 17 watts of energy. Alpha is the albedo, so alpha times S0 pi a squared is being reflected back to space without doing any work on Earth or in the atmosphere. So the net energy that remains is then what is intercepted minus what is reflected. So S pi S0 pi a squared minus alpha p times S0 pi a squared, so 1 minus alpha. That gives you 1.22 times 10 to the 17 watts. If we remember that the average albedo of the Earth, we are doing the whole globe, so we look at the average albedo, so we average over all these things, which gives us 0.3. That gives you a number of 1.22 10 to the 17, and Earth is receiving this energy. Land is getting heated, evaporation over the ocean, clouds are forming, etc. And there is a net loss of energy back to space as a black body. Black body is something that has no ability to reflect, so it absorbs energy based on various properties, and the emission depends on its temperature to the power of 4. So sigma is a constant times Te to the 4th. Te is the effective emission temperature. Okay, so that's black body radiation, or the Stefan-Boltzmann law. And we know what the constant sigma is. So the emitted terrestrial radiation for the entire Earth is obviously from every point on Earth's surface, which means you have to multiply it by area of the sphere, which is 4 pi a squared. So each unit area is emitting sigma T to the fourth, and all of Earth is emitting 4 pi a squared sigma T to the fourth. You equate 2.1 to 2.21 equation 21 to 23, and you end up with effective emission temperature of S0 1 minus alpha P, or 4 sigma. So it depends on incoming energy, effective albedo, and sigma, the Stefan Boltzmann constant, which gives us emission temperature of 255 Kelvin. This is the emission temperature, not the surface temperature. Okay, so whatever is being emitted from the atmosphere to space, and that, as we saw in the last podcast, is the effective emission temperature of Earth. But what is surface temperature? This is where the greenhouse effect becomes critical. We'll see that a greenhouse effect determines how warm the surface will get based on how the energy balance is happening and how that energy is being distributed within the Earth's atmosphere. Okay, so let's look at a little bit more about black body. If you look at the normalized wavelengths versus normalized frequency or energy versus wavelengths, then the sun's energy is being emitted at an average temperature of 6,000 Kelvin, whereas Earth is at 255 Kelvin. And you can see that the wavelengths are distinctly different for the sun and the Earth. Sun is producing its own energy, and it's emitting very brightly at the visible spectrum. So wavelength is right in the middle of the visible spectrum, whereas Earth is far off into the infrared or long wavelengths, right? So how does that get distributed within the atmosphere? I'll do that in the next podcast. Basically, we need to look at the gases that are in the Earth's atmosphere that determine which wavelength goes through and which wavelength tries to go out but is not allowed to go out completely, is absorbed, changes the energy of the or temperature of the gas that's absorbing it, and it's that temperature that determines how much energy goes out. Always sigma T to the fourth for bodies that are absorbing energy and emitting them, right? Very simple, so just track them. Simple concepts, but you just have to track them properly.